is Kevin Weekly. I work under Professor Alex Byan, and our goal as part of the SinBerBest project is to develop a model tying together data from sensors to occupant comfort.
Understanding that observing a system goes hand in hand with modeling that system, setting up the server which will accept and process sensor data was the first priority. We designed the system from an experimental perspective, in that components, such as algorithms, are easy to swap in and out and configure, all without being disruptive. Concurrently, we have considered how to interpret incoming sensor data. As of now, device-level power usage has been our focus, such as the trace shown in the top figure. The first step is to apply signal processing techniques such as a sliding window min filter and spike suppression to remove noise from the data. The next step is to interpret that data via a model, such as a hidden Markov model. An example, such as the traces shown at the top of this slide, is that using a model we can distinguish the power usage of individual devices sharing a single sensor. However, we first had to determine values for the parameters of the model, which is where learning comes in. In particular, we have designed custom hardware to measure the power usage of individual devices, shown in the below figure, so we can populate the parameters of the model.
With a comprehensive mathematical model of the building, we hope that this will help us reduce the inputs to the system, that is, the energy consumed by the building, while also optimizing the outputs of the system, that is, the occupant comfort in the building, leading to a win-win situation for both building managers and occupants.
Hi, my name is Claire Tomlin, and I'm a professor in electrical engineering and computer sciences at Berkeley. And I've been working on a project with my postdoc, Anil Aswani, related to energy efficient HVAC, heating, ventilation, and air conditioning control, which we would like to apply to tropical buildings in Singapore. I'm just going to say a few words about the project and what we've done so far at Berkeley. So the basic idea behind our project is to use the existing HVAC infrastructure in a building, yet to apply a control scheme over top of the existing controls. So we typically would use our scheme to actually implement the control algorithms that already exist in the building. But what we do is we use a scheme, or we've designed a scheme, which we call learning-based model predictive control, where model predictive control is a scheme that makes guarantees on the state variables in the building to make sure that they remain within certain bounds. For example, the temperature remains within certain bounds, the humidity remains within certain bounds. And the learning-based component is the part we've updated, or we've adapted model predictive control to include this learning-based component. And what we mean by that is we collect data as the scheme is implemented. We collect data about the building, about the temperature changes, and then we use that data to update the actual model that we have of the building in this model-based control scheme. So this is a very useful technique if you have a good idea of the physics of the system, so you build an initial physics-based model, but there's a component of the system that needs to be identified from data. So in buildings, this is typically occupant behavior, how spaces are being used over different times by the occupants. What are the trends? What are the patterns? What do occupants prefer? And so as we're controlling the system, we're guaranteeing that the state variables remain within bounds. That's the MPC part. But at the same time, we're learning a better model of the system, and we're using this to get, in the end, a higher performance control scheme. And for us, higher performance basically means higher energy savings in the system. So far, we've implemented this scheme. We've designed it and implemented it in 2 spaces in the Berkeley campus. We have a single room space in Corey Hall, which has its own HVAC system. So it's like a house type of environment. And then we have a larger building, Sutarja Dai Hall, where we have all 7 floors of mixed-use space that the scheme is controlling. And in both spaces, we've spent some time identifying a nominal model of the system, and then we've implemented over periods of time the learning-based model predictive control scheme, and we've learned better models, and we've then compared our results in terms of energy savings with the standard thermostat-based control, which is currently used in both spaces. as I said, the modeling method, the learning method, is learning the unknown dynamics, so what's not included in the physics-based model. And in our temperature-based model, that's the kind of, what we call it, the heating load. Everything that doesn't come from the inherent physics of the space or of the control inputs or of things that we can measure, like the effect of outside temperature on the space. So things that we have a good ability to measure. The heating load, the part that we identify, comes from learning, and this is largely, as I said, occupant behavior, how occupants affect the overall temperature in the system. We've applied this scheme to these two spaces in Corey Hall and Sutarja Dai Hall, and in both cases we've achieved significant energy savings. And so we have a method in which we apply the scheme, we collect the results, and then we simulate the other control scheme, in our case the thermostat-based control in that same space, and then we compare with those same conditions, and then we compare them, and then we flip. We implement the thermostat-based control, and then we simulate our learning-based model predictive control. And as I said, in each case we've got significant energy savings. Forward with this, we look forward to applying it to the kinds of environments in Singapore. So tropical buildings, different kinds of HVAC control schemes. The technique is very general, and it will allow us to incorporate these different models, different parameters, different environments. Thanks very much.
My name is Kameshwar Phula, and I am with Departments of Mechanical Engineering and Electrical Engineering at Berkeley. And I am really excited about the SinBerBest project. I think it offers us a very unique opportunity to work with very talented students and professors and engineers in Singapore and do experiments at a scale we cannot imagine here at Berkeley. I'm involved in 3 separate projects, all in the controls thrust in SinBerBest. And I'm going to talk to you about one of them, which is lottery incentives for residential demand response. So I'm going to tell you about one of our projects, which is managing demand. So we can view buildings, either residential buildings or big office buildings, as a resource for the grid. And today, demand, whether it's residential or commercial, is treated as inelastic. So it's power on demand. You turn on a switch and you expect to have your lights go on. But if you can manage the demand side, you can offer significant value to the grid. For example, in peak shaving, if there's a shortage of energy available, you could have buildings cut back on their energy consumption so that everybody's met their power needs. There are many other ancillary services, such as energy efficiency, regulation services that buildings can provide. If I look at residential units, the value of each home, if you like, for these to the grid is on the order of $30 per month per household. This is a very small number. But when you add it up over tens of millions of households, it adds up to a very large number. So there's certainly a lot of value for the grid in extracting demand response. The current approach is direct load control, where the grid controls the load. And there are dynamic prices like time of use or rebates for participation. And the price signals tell you when and how to extract how much demand response is needed, and the prices reward participation. But the problem is $30 a month is a very, very small number. Let's say a portion of this is given away to the household and another portion is sent to the grid. And it'd be very hard for a household to get excited about such a small reward. So incentivizing customers to participate in demand response is a big challenge, and that is what our project is about. And our approach is to use lotteries. So instead of, say, offering a participant $20 a month to participate in demand response, we offer them, say, $2,000, but with 1 in 100 chance. This leverages on, if you like, the greed of consumers, and we believe it will really incentivize people to participate in demand response programs. Indeed, there are a lot of other studies, for example, at Stanford, to show that lotteries help in recycling, the Instant Project, another project in Singapore to encourage consumers to commute in off-peak hours. So it's a very powerful tool. So what we want to do is to do experiments, say with 10,000 households, to show that you can get load reductions induced by lottery incentives. We want to develop the hardware and the software to enable demand response using lottery incentives. And the basic hypothesis we want to test is a lottery incentive is capable of inducing a much larger mean demand load reduction and much more reliably, with much less variance, than fixed rebate-based incentives. We're working with a very talented group of people at Singapore, Professor Su Rong, Professor King Jet, and some students we've recruited. And I look forward to spending a good chunk of my research time and energy in Singapore. And I've already spent 5 months, and it was a wonderful experience, and I found it to be very, very rewarding.
I'm Alberto San Giovanni Vincentelli of the University of California at Berkeley in the Department of Electrical Engineering and Computer Science. And my role in the project is to lead thrust number 3, which is about building operating systems. That is to say, the set of algorithms and infrastructure that is used to manage and to optimize the behavior of the building. So the motivation for our research on building operating system is related to the fact that much energy is wasted in buildings, and buildings are responsible for a majority of use of electricity and gas in the United States. And we believe that this waste can be reduced dramatically by being more intelligent about the use of energy and sensor and controls that are in the building itself. The situation today is that we experience poor controls design. There is no modeling or optimization of what goes on inside the building. There is a poor implementation of the control algorithm that have been implemented. There is a lack of commissioning of the building itself. There is no full diagnostic that is automated, and there is almost no information transfer from design to construction to operation. If we want to optimize the operation of a building, we have to cope with all these problems. So the goal of our research project is to apply new foundation and methodologies to develop this set of programs and infrastructure that we call building operating system that is capable of fundamentally changing the consumption in the building itself, so that we have an agile and adaptive consumption of energy in the building, and particularly in the form of electrical power. So we concentrate on electrical power point of view. We would like also to provide a high degree of cooperation between the building and the extended smart power that the network, the distribution network provides. And we want to incorporate as much intelligence as possible to the various points where the energy from the grid is consumed inside the building. We also want to make sure that the critical functionality is available at all times in the building, even though there may be false errors, accidents in the building itself. Now, how do we plan to accomplish this? We would like to use pervasive instrumentation, like the one offered by wireless sensor network, broadly embedded intelligence, so computing entities all over the building itself, the design of communication and control schemes that are robust and can optimize the behavior of the building itself, and then forecasting and planning to manage the load that the building present to an intelligent energy distribution grid. Now, the architecture of the system that we plan to build is depicted in this slide. where we have the essential part of the scaffolding of the building itself, is of the infrastructure of the building, are 3 buses: an external information bus that connects the intelligent grid to the building itself, a user information bus that is used to convey the information about the operation of the building to a manager or to the people who are in the building, and then finally physical information bus that is responsible to convey the results of the data measurements towards the external and the internal operation. Now, inside this box, of course, there are all the various equipment that are in the building itself, and the interfaces that provide reading of key performance parameters that are then controlled by the control algorithms and are distributed using the communication schemes that we have presented before. Everything has to be optimized so that we can demonstrate that we reduce the use of energy while maintaining the comfort parameters that we are set to provide to the building. So in conclusion, we are very happy about the potential of testing our ideas about building operating systems in a country like Singapore, where we have access to all kinds of buildings and infrastructure that we can play with.
Bill Nazaroff, a professor at UC Berkeley, and I'm co-leading the Thrust 4, which is called Human Building Interactions in the Environment. The mission of this thrust is to acquire information, create knowledge, and to convey understanding to ensure that indoor environmental quality services are provided even as we approach improved energy efficiency in buildings. So our program has 2 main areas of focus or emphasis. One is to ensure thermal comfort is provided for building occupants in an energy efficient manner. And the second is to protect occupants in buildings from excessive exposure to indoor air pollutants. To understand the second issue, it's helpful to consider a simple model for indoor pollutants in which the indoor concentration is made up of the sum of 2 parts. One is a contribution from outdoor pollution that is brought in along with the ventilation air. And the second part comes from emissions from indoor sources that are diluted and that may decay because of processes occurring within the building, such as removal by ventilation. The principles for effective indoor environmental quality control really come down to 4 main points. The first is that we have to limit the emissions of pollutants from materials and processes that occur in the indoor environment. The second is to take appropriate measures to protect the building occupants from outdoor pollutants, such as particulate matter from fires. The third is to provide adequate ventilation so that whatever residual pollutant emissions occur in the indoor environment don't build up to too high a concentration. And then finally, the fourth key is to apply air cleaning as is necessary. Thrust 4 is divided into 4 work packages. The first of these focuses on the hygiene of heating, ventilating, and air conditioning systems. The problem that we're concerned with is that there may be some mold or mildew building up on the interior surfaces with air conditioning processes, and these can degrade indoor air quality. The second factor, the second work package, is concerned with human factors for thermal comfort. So here, the interest is to consider whether in a hot and humid tropical environment, people might have different degrees of adaptability or adaptation to warmer conditions than the standard that's normally applied for thermal conditioning. Third, we're concerned and interested in bioaerosols in tropical buildings. The warm and moist conditions mean that mold and condensation occurring on indoor surfaces can lead to degradation of indoor air quality. And then finally, because many of the issues of concern involve changes in temperature and humidity to improve energy efficiency, we want to be attentive to how those conditions may affect indoor pollutant dynamics. So in summary, the high-performance buildings that we seek must have good indoor environmental quality to achieve their purpose. Energy efficiency and good indoor environmental quality requires improved understanding of the key issues. Knowledge gaps in tropical climates include ventilation system hygiene, thermal comfort criteria, bioaerosols, and the effects of temperature and humidity on pollutant dynamic behavior. Thrust 4 will add knowledge that will advance indoor environmental quality science and improve building practice.
Project is part of Thrust 5, and we are focusing on the development of a high-performance green concrete for energy-efficient buildings. Now, concrete is the most widely used construction material for buildings in Singapore, but unfortunately, the production of concrete, specifically the production of one of its constituents, which is Portland cement, is a very energy-intensive process. So the production of Portland cement for each ton of cement requires 5 gigajoule of energy, and each ton of cement that is being produced emits 1 ton of CO2. The objective of our project is to reduce the embodied energy and the environmental impact of concrete buildings. We are focusing on replacing up to 50% of cement by industrial waste materials to reduce the carbon footprint and energy consumption of concrete. We are replacing aggregates by recycled concrete to reduce the consumption of raw materials and to reduce Singapore's dependency on import of aggregates from other countries. And we are increasing the surface life of concrete so buildings last longer and need less repair and maintenance. For that, of course, we need a concrete that is crack resistant. So to achieve our objectives, we are developing a high-performance green hybrid fiber reinforced concrete composite. The performance of this high-performance high FRC in flexure with and without steel reinforcements is shown here. Whereas concrete fails in a brittle manner, at relatively low strength, the high-performance high FRC exhibits higher strength and higher ductility due to its deflection hardening behavior. This deflection hardening behavior is essential for crack resistance and damage resistance. The high-performance green high FRC will combine many important features: reduced energy consumption, reduced greenhouse gas emission, and enhanced performance in regards to long-term durability, crack resistance, and damage resistance. So here are 2 examples that illustrate the crack resistance and damage resistance of high-performance high FRC. When reinforced concrete and reinforced high-performance high FRC are loaded and cycled at the same surface load, the reinforced concrete cracks, whereas the reinforced high-performance high FRC is successful in resisting crack formation. This crack resistance will ultimately enhance the durability and surface life of concrete buildings. When concrete and high-performance high FRC panels are hit by a steel projectile, the concrete panels fail catastrophically, whereas only small microcracks are present in the high-performance high FRC panels despite higher impact velocity. Therefore, even under such severe loading conditions like impact loading, the high-performance high FRC exhibits crack and damage resistance. Products that utilize high-performance green high FRC composites will reduce the embodied energy of concrete buildings, and because they are more durable and more damage resistant under surface load conditions, they will last longer and require less maintenance and less repair.
I'm Paulo Monteiro, a professor in the Department of Civil and Environmental Engineering at the University of California at Berkeley. We are very proud of our long tradition in developing state-of-the-art concrete, but we are dealing with something even more fascinating, developing concrete to be used in the Singapore projects, and I'm fortunate to work together with outstanding faculty researchers at NUS, Professor Ming Hong Zhang and Leah Yu. Here is our scientific roadmap. Our goal is to make concrete as a new multifunctional building material in which we will have fantastic energy savings, make the concrete more durable, also self-clean, and with better atmospheric conditions. For that, we will propose to develop a concrete with very low thermal conductivity and develop photocatalytic coatings, both for visible light indoors and outdoors. Our approach will be to integrate energy efficiency as a structural material such that the material will be lightweight, will have low thermal conductivity, and at the same time have enough strength and elastic modulus to provide enough mechanical strength. This material also have a fantastic environmental and sustainable performance. This is the research that we are conducting at the moment. We are very fortunate to have the best ambient X-ray photoelectron spectroscope in the world. This work has been done together with top scientists that allow us to study the chemical reactions and photolytic reactions in real time and ambient conditions. Very few facilities in the world can do that, and we are very lucky to have it at Berkeley. And at the moment, even though we are at the beginning of the research, we got fantastic results because it indicates that this new and unique technique that we developed here in Berkeley can permit us to study the reactions in real time with high precision and can allow us to optimize the formulation of a fantastic new material. Joint work would allow us to develop new technologies that would have a great impact in the construction industry. I look forward to the opportunity to work together with students and colleagues in Singapore, and I welcome all the researchers and students to come to Berkeley. Thank you.